Okay, believe it or not, this is actually the last thing in this unit, the last new thing, but it's maybe one of my most favorite of things. So, logarithmic differentiation. So, we are actually going to find the derivative of this bad boy. Now, you don't have to use logarithmic differentiation to do this. You could use quotient rule. Within quotient rule, you would have the chain rule several times. You would have an E rule, you would have a sine rule. So you could do the derivative like we already know, but it's not very fun. It's not as fun as logarithmic differentiation. So what we do when we're doing logarithmic differentiation is we take a very complicated function and we actually apply the natural log to both sides. And the next thing we do is we use laws of logs to simplify this, okay? So law of logs tells me if I have two things divided, I can write them as a subtraction. So let's just start with that part. Then there's another law of logs that tells me if I have two things added to or multiplied together, I can write it as an addition. So let's use that law of logs. Instead of writing this as a square root, I'm just going to take it and write it like power of a half. Now, this is a really common mistake. This is subtracting everything after here. Using law of logs, because this is multiplication, this becomes an addition. But because it's a subtraction here, the subtraction distributes. Okay, one more law of logs. I can use the law of log about exponents. If I have an exponent here, it can become a coefficient. Isn't this pretty? Now, so this is the natural log of y equals this whole thing. Now I'm going to use implicit differentiation to find the derivative of everything. So I'm going to apply d dx to both sides. So when I apply d dx to this side, I'm finding the derivative in terms of y. So it's the natural log of y, the derivative is 1 over y, but I need a dy dx to hold the spot. Equals. Okay, natural log of b is 1, so I don't even, this is like a coefficient. The derivative of x is 1. Plus, so here I have the derivative of the natural log, so the derivative is 2x over x squared plus 1, and it's all multiplied by a half, that was the coefficient, minus 3 times 2x all over x squared plus 2, so I'm just using how I find the derivative of a natural log there, minus the derivative of sine x is 5 cos 5x over the original. Okay. Now I need to do some simplifying, okay? So, first of all, I want dy dx by itself because that's the derivative, so I need to get rid of this 1 over y. So I'm going to multiply both sides by y. So I end up with dy dx equals y times, and as I rewrite this, I'm going to simplify it. 1 plus, this and this cancel, so I have x over x squared plus 1 minus 6x over x squared plus 2 minus 5 cos, oh, it should be 5x. 5 cos 5x over sine 5x is going to be 5 cotan 5x. Okay, so that whole thing is multiplied by y. So I'm almost done, but believe it or not, I'm not done yet. Because I'm looking for dy dx, the derivative of this. The derivative of this should not contain a y. But luckily, I know what y equals. Y equals this big extravagant thing up there. So the very last step is to plug in the original. So I end up with dy dx equals y, which is the original question, times that stuff down there that I already simplified. Now the coolest thing, I mean there's several cool things about logarithmic differentiation, but one of them is that you've already simplified your function. Like it doesn't get any simpler than that. It's basically like already has everything factored out of it that is in common in each piece. So I think it's pretty beautiful. I hope you enjoy logarithmic differentiation as much as me.